So hello everyone, in this video we will look at a problem from electrostatics from the book Introduction to Electrodynamics, very popular textbook for electrodynamics. You can pause the video here, you can look at the problem if you haven't already and try to solve it on your own. It's a very interesting problem and it has to do with taking limits. So it's a fairly mathematical problem. So let us look at it. We are given an ellipsoid shaped conductor. So an ellipsoid is a particular type of solid, and of course if it's a conductor, all the charge that we give to the solid will go to the surface. And the equation of the ellipsoid is given over here, and the charge distribution, the surface charge density over the surface of the ellipsoid can be derived exactly. So he says that when we have a arbitrary shaped conductor, it's extremely difficult obviously to find the exact expression for the surface charge density, but in the case of an ellipsoid we can derive it exactly. We are not going to look at the derivation here, but we are going to look at how we can use this result to get a bunch of other results. So basically we are given three different types of surfaces, not surfaces exactly, I would say three types of objects. So the first object we are given is a circular disc in the XY plane. So before going into what we have to do with this formula, let us look at what an ellipsoid is. So an ellipsoid is this, you can say it's a generalized sphere. So what I mean by a generalized sphere is that a sphere is only a special case of an ellipsoid. So in the case of a sphere, these quantities A, B and C would all be equal, and they would be equal to the radius of the sphere. But in this case, this is an object which has three different radius, values of radius along the X, Y and Z axis. So basically along three mutually perpendicular axes, it has three different quantities that act as the radii. Right. So if you like the limits of the ellipsoid go between, if you look at the x-axis, the span of the ellipsoid is between x equal to minus a here and x equal to plus a over here. Similarly on the y-axis it is y equal to plus b over here and y equal to minus b over here. So the farthest it can go from the origin along the x-axis is a, that distance is a, and the farthest it can go along the y-axis from the origin is b. And you can look at it from this formula also, that this is a bounded sort of object. Why? Because if you want values of x higher than a, then if you put a value of x which is higher than a here, then no real values of y and z will satisfy the equation, because if you take x square by a square to the right hand side, it will become negative. So just trying to get a feel for what an ellipsoid is. I'm just talking about it because I want to convey the idea that it's not a very difficult concept to understand. Another property we can look at it for an ellipsoid is if we cut a section. So if I cut a section like this, perpendicular to the x-axis. So if imagine a plane which is perpendicular to the x-axis and it cuts the ellipsoid, then the points at which the plane will intersect the ellipsoid. So remember that the ellipsoid is a surface, it's not a solid. We're not talking about the volume inside, we are only talking about the surface. And this equation that we're given, this equation is also for just the surface. So if we imagine a plane which is perpendicular to the x-axis, let's say at x equal to minus a by root 3. So that would lie somewhere over here. So if we have a plane which is parallel to the yz plane and perpendicular to the x-axis, then that plane will intersect this ellipsoid along certain points, and those points will trace out an ellipse. It's not very difficult to understand that, if that plane cuts this object, we will get an ellipse, and we can show that mathematically, that if I put x equal to a minus a by root 3, I get this equation which is an ellipse, and this ellipse is in a plane which is parallel to the yz plane, right? X is already fixed. We fixed x. We put the value minus a by root 3. So we are in the plane. We are in the plane x equal to minus a by root 3, and in that plane we have an ellipse. So in 3D geometry, if we have just one equation, so for example, if I have this one equation, it describes a surface, right? Just like in two-dimensional geometry, if I have an equation, I need if I have an equation, it describes a curve, a straight line, a circle, a parabola. Those are curves, and curves are described by one equation in 2 dimensions. Similarly, surfaces are described by a single equation in 3 dimensions. But if I want a curve in 3 dimensions, I will need 2 equations. So for example, if you have studied 3D geometry, you would know that in 3 dimensions, to describe a curve, you need to describe a straight line, for example, you need 2 equations. But to describe a plane, you need only 1 equation. So to describe that ellipse that is produced by cutting this by a plane parallel to the yz plane, we get an ellipse, and that ellipse is described by these 2 equations. You will need both these equations to tell you which points. So which points are those which lie on this ellipse, which satisfy both these equations, right? So enough about the ellipsoid now. So let us jump into the problem. So what we have to do with this ellipsoid in this problem is that we have to choose appropriate values of a, b and c. So if I take just random values of a, b, c, I get an ellipsoid. If I choose like a equal to 1, b equal to 5, c equal to root 3, something like that, I get an ellipsoid. But if I choose particular values of these quantities, I get particular shapes. For example, if I choose a equal to b equal to c, I get a sphere. That's a very simple example, right? Similarly, in this first case, if I want, so he is saying find the surface charge density on a circular disk of radius r. Right? So how can the ellipsoid become a disk? Right? Just by choosing appropriate values of a, b and c. So if I put the disk in the xy plane, I can put it in the yz plane also, but for convenience I put it in the xy plane. It is centered at the origin, just like the ellipsoid. Ellipsoid is also centered at the origin. So if I put it in the xy plane and it's a disk, so its dimensions along the z-axis must be 0. So the c, the parameter c has to go to 0, and the parameters a and b have to become equal. If a and b are not equal, so suppose I make c equal to 0 first. So concentrate on this equation. If I make c equal to 0 first, right? Don't think about what the equation becomes just now, but just think of how the shape will change, right? So if I make c very small, if I keep making c smaller, the ellipsoid will keep flattening and will flatten onto the xy plane. Nothing will remain which is outside the xy plane, and it will become an ellipse. It will become an ellipse in the xy plane, right? So so by choosing the quantity, the value 0 for c, I flatten the ellipsoid into a disk in the xy plane. If I want a circular disk, I choose a equal to b equal to r, right? So how would that affect the formula for the surface charge density is what we want. We know what we have to do with the quantities A, B and C to make it a disk, but how to derive the surface charge density of that disk from the given formula. So this is the given formula for the surface charge density on the ellipsoid. So if I just put in C equal to 0 here, then this will go to infinity, and it doesn't make sense. So the outside, this what the quantity outside is also going to infinity. So I just transform this formula first into a form. I transform it into a form where if I apply the limit C is going to 0, I get a meaningful answer. So that is my process. So first what I do is I try to get rid of this Z, right? Because what I realize is the final formula that I will get for the charge density, that charge density should only depend on X and Y. It has no meaning of depending on Z. You cannot expect it to depend on Z, because the resulting body that we are going to get, the disk that we are going to get, it will have no Z dimension. The Z of all the points on the disk, the Z coordinate of all the points on the disk will be 0. So the surface charge density will not depend on Z. That is very clear. That is extremely clear. So we might as well get rid of it. That is my, you can say, clue that I need to get rid of Z. So I just use this ellipsoid equation and I get rid of this Z. So at this point, don't think that C is 0. Just think that this is a normal ellipsoid and we are just transforming the equation for the surface charge density by this replacement. Don't think that C is 0 yet. So we get this. I just put Z equal to Z square by C square over here. I put A equal to B equal to R here, so I get this. Now moving on, I have a C outside. So here I have a C outside, and inside, so I'm starting to think that I want to take that C to 0. So what do I have to do for that? How can I get a meaningful result? So if I put C0 here, obviously this will become infinite, won't make sense. So I take this C inside so that I get all the C's in one place. So this C goes inside, and of course there's a power minus half, so that C in the denominator becomes C square in the numerator, and this is what we get. And now we can do it. Now we can just put C equal to 0 and we are going to get a meaningful answer, because this will go to 0 and there are no other terms which are problematic anymore, so we get an answer. So we can put the limit C goes to 0. So at this step it is still an ellipsoid. At this step it is still an ellipsoid, and this is a special kind of ellipsoid where A is equal to B is equal to R. That is all I have done, and this is the surface charge density in terms of the X and Y coordinates. But if I bring that C quantity to 0, I get this answer, which is in the third line. Very simple to see that the limit works. C goes to 0. X square plus Y square, we are in the XY plane, we are on a disk, and X square plus Y square in the XY plane is just the distance squared from the origin, because we are now moving only in the XY plane. We are on the disk now. So X square plus Y square is the distance squared from the origin, and therefore this is the final result. The small r is the distance from the origin. So this is the surface charge density on a circular disk, on a circular conducting disk in the XY plane. And another thing that I did over here is I multiplied the whole result by 2, because this surface charge density in this step marked by the red dot, this surface charge density is on only one side of the disk. So the disk now has two sides. So if I look from the positive Z axis, I see one side, and if I look from the minus Z axis, I see the other side. So this is the surface charge, because just think about it. the ellipsoid was flattening more and more as I made C very small, C is approaching 0. The ellipsoid is flattening, so it still has two sides. It has an upper side and it has a lower side, and that is the surface charge density that we get. It's the surface charge density on one side of the disk, but if I multiply it by 2, I get the total charge density. So what this formula is telling us is that if you go a distance r from the center and you get a point at that in a small area element, so this is the surface charge density, charge per unit area. So if I go to a point which is at a distance small r from the center of the disk, I take a small area element, and that I take the same area element on both sides of the disk, on the upper side, on the lower side. I find the total charge in that area, and this is what I get. This is the total charge in both of those areas combined. So this is the total charge density on both sides added up, right? So if I integrate it, so if I take a ring element of radius r and I multiply that area with this surface charge density and I integrate it over the entire disk, I should get the total charge. Whereas if I had not multiplied by 2, if I had 4 pi r in the denominator, I would be getting the surface charge of only one side, which would be q by 2. So you can check this on your own. You will get the total charge, which is q. So now moving on to the second part. Again, we have an object that we have to reach through some transformation of the quantities A, B, C. We have an ellipsoid to begin with, and we want a strip. So let us read. Net surface charge density on an infinite ribbon in the xy plane which straddles the y-axis. So straddles the y-axis means that its boundaries on the two sides are parallel to the y-axis. So this is one side which is x equal to minus a, and the other side x equal to plus a, and it is a ribbon in the xy plane. So it has no z dimension, so it is a flat ribbon. It's a planar ribbon in the xy plane, but its length in the y direction is infinite. So in this direction it goes on, and in the minus y direction also it goes on, but in the x direction its width is only 2a. So this is the kind of ribbon that we want. So at first go, it might seem very surprising that how can we reach this infinite body starting from an ellipsoid, but we can make ABC whatever we want. We can make them infinity as well. So of course, because we are in the xy plane, so C must be going to 0, because again the z dimension has no existence here. The z dimension is going to 0. C will go to 0 and B will go to infinite. So what I have drawn over here, these two figures. So this is the figure. If I just make C is equal to 0, I get a planar ellipse in the xy plane. C has been made to go to 0. There is no z dimension anymore. The ellipsoid has been flattened onto the xy plane. C is extremely small. It's practically 0, you can say. So it will be, as C is made smaller and smaller and smaller, this ellipsoid will approach a flat elliptical disk in the xy plane, whose width is 2a, whose height is 2b. So this height would be 2b. And now if I want to go from here to here, if I want to go from this ellipsoid, which is a finite disk, to this finite elliptical disk. Now if I want to go from here to this ribbon, the B will go to infinite. But what do we mean by the third line over here? So there is one difference, important difference from the first part, and that difference is that here, because the size of our body is infinite, we also have to make a change to the total charge on the body, because in the initial formula for the ellipsoid, the total charge on the ellipsoid is given as q. Of course, the total charge on the ellipsoid is a finite charge. But if the ribbon is infinitely large and there is a finite surface charge density, the surface charge per unit area is a finite thing, then the total charge would become infinite, and therefore the total charge has to be gotten rid of, and the total charge has to be replaced now with a new quantity which we are given, which is lambda. So here we are given this capital lambda over here, and this is the total charge per unit length of the ribbon. So what do we mean by that is that if I take a unit length in the y direction, the charge on that unit length would be capital lambda. Right. So now, why have I said that lambda approaches the value q by 2b as the length of the object becomes infinite? Why is it not initially q by 2b? So if I look at this ellipse and if I look at a unit length, if I look at a length dy, so if I make a section over here, so if you imagine two lines parallel to the x-axis cutting across this ellipse, and a length dy intercepted between them, if you look at the charge on it, the charge on it would be different from over here, and it would be different over here, right? So the total charge that is on a unit length, on a length dy, let's not call it a unit length, let's call it an infinitely small length dy. So the total charge on a very small length dy, the total charge between the line y is equal to, let's say, y1 and the line y equal to y1 plus dy. So the length intercepted between those two lines would be dy, and the total charge intercepted between those two lines would be the charge per unit length. But that charge per unit length would be different everywhere. So if I keep those two lines, those two parallel lines close to the x-axis, it would be the charge intercepted would be different, and here it would be different. But if I do the same thing on this infinite body, because it has now become infinite, any point on the y-axis is just equivalent to any other point on the y-axis. So the charge per unit length would become uniform, right? And the total charge, if the total charge was initially q, right, the charge per unit length, you can say the average charge per unit length on this ellipsoid shaped disc was q by 2b. Why? Because the total charge is q and the total length in the y direction is 2b. So the average charge per unit length on this ellipsoid shaped body is q by 2b. But that value is not the same everywhere. It's just the average. It's different everywhere. Charge per unit length is a varying quantity. As you move on the y-axis, if you move a small distance dy in the y-axis direction, and I ask you how much charge did you encounter? So if you draw two lines parallel to the y-axis, and there is a distance dy intercepted between them, what is the total charge between them? It would be different depending on where you draw the lines. In contrast, if you draw those two lines on this ribbon, it would be the same all the way through, because now there's uniformity. It's just uniform. There is no way you can distinguish between 2 points on the y-axis on this ribbon. So the average value of this charge per unit length on this ellipsoid would be q by 2b. But as you stretch it out, as you keep making b larger and larger, q would keep increasing, b also is increasing. Obviously you are increasing b, and to as you make the object larger, you're obviously increasing the charge also, because the surface charge density needs to be kept finite, and the charge per unit length also needs to be kept finite. So if you keep increasing b but don't increase q, the charge per unit length would become very small. It would go to 0 as you make the length very large. So you are increasing q and b both, such that when you have increased b to a very large value, the charge per unit length obviously has become uniform, and as it becomes uniform, it approaches this constant value, which is capital lambda. So you're increasing q and b in a particular fashion, such that the charge per unit length becomes a constant value, capital lambda. It would of course become a constant over the entire body, right? It could become 0 if you don't increase q. If you don't increase q but you keep increasing b, ultimately the charge per unit length will become 0 everywhere, but it would become a constant because of the uniformity of all the points on the y-axis. So this is a very interesting part. So q by 2b is a ratio which approaches lambda as the length becomes very large. So with that knowledge, we can now proceed to finding the limit. So we start with this formula for the ellipsoid, and what I do is I separate out this q by 2b, because this q by 2b is something that is approaching a fixed value. I know the rest of the thing. In this rest of the thing, c is going to become 0, I know, and b is going to become infinite. But in this form, the limit is not very easy to see what's the answer going to be. It's not a very meaningful result. So we have to make some changes. So what change I made is I took this c inside, and I took the limit q goes to infinity and b goes to infinity over here on this, because of these two things being in a product, they will not affect each other, because this q by 2b is separated from the rest of the product, and this q by 2b is anyway approaching a finite value. It is not going to 0 or infinite, so it is not going to mess up or disturb the rest of the expression anyway. So we might as well just write it as lambda over here. This is not the most ideal way of doing it, but it makes sense mathematically. It makes a lot of sense, and we're doing it because we want to keep it simple. We could have done it the long and complicated way, but let's not do it that way. So we are left with this part. We have taken c inside, and we are left with this expression in which c is going to 0 and b is going to infinite. So c is going to 0 makes this third part infinity, and again, because we don't have an xy direction, we don't have a z dimension anymore, so we might as well eliminate this z, because we know that the sigma will not depend on z. So the z is taken out using the ellipsoid equation, and we are left with this expression. So if I rewrite it, I get this. So lambda upon 2 pi a times this whole expression, and all I've done to get to this point is I've taken the c that was outside inside, and I have transformed this z square by c. I've changed this z square by c square using the ellipsoid equation. So I get this very comfortable limit where c is going to infinite, c is going to 0, and b is going to infinity. So b is going to infinity makes this part 0, b is going to infinity, c is going to 0 makes this part 0, this part also becomes 0 because c is going to 0. So we get this simple result, and this again I multiply it by 2 because again the ribbon has two sides, and when we flattened the ellipse ellipsoid and made one dimension infinite, the ellipsoid still has two sides. So if I look from the positive z-axis, it has the ribbon has an upper surface which is visible from the positive z-axis, and the ribbon has a lower surface which is visible from the minus z-axis. Both these surfaces have their own surface charge density. So this formula over here in the second line on this page describes the surface charge density on only one side of this ribbon. So if I want the total charge density at a particular coordinate x, so what is the meaning of this formula in the box is if I go a distance x from the origin, I get a point. If I take a small area around that point, in the neighborhood of that point, small area element in the neighborhood of that point, and the same area element on the other side. So if I take the same area element on the upper surface of the ribbon and also on the lower surface of the ribbon, the total charge on both these surfaces would be lambda upon pi times under root a square minus x square. So again, we will have to check that the total charge in a unit length. So total charge in a unit length, how would we calculate that? So if I just integrate over the entire span from minus a to a, if I multiply it by the length, so basically you can understand that this is the total charge, this formula in the box, this is the total charge on a small area element whose dimensions are dx and dy. Just think about it like this. So on any point on the ribbon, there is an area element whose dimensions are dx and dy, right? And this is the total charge on that area element. So if I now multiply this surface charge density, if I integrate the surface charge density over all the dx's, right, then I will get the total charge contained in a strip which is confined between y equal to y and y equal to y plus dy. So why I have not included a diagram over here is because you should be able to draw this diagram on your own. I'm just giving you hints, I'm just pointing you in the right direction that you should draw a diagram and think for your own self that what is this lambda. I have given you that lambda is equal to a particular integral here, but what was lambda? We have discussed in length a few minutes ago. What is lambda? So lambda is the charge per unit length in the y direction. So if I say charge per unit length, you can measure that length in the x direction, you can measure that length in the y direction, but this length is because the charge per unit length in the x direction would be infinite. So if I am at a particular coordinate in the x direction, and I say that x equal to, let's say, a by 2 and x equal to a by 2 plus dx. So between these two boundaries, what is the total charge? So there are infinitely many points. There is an infinite length in the y direction that lies between these two coordinates of x. Between these two x coordinates, there is an infinite length in the y direction that is present. So the total charge will be between those two x coordinates will be infinite. But between two y coordinates which are dy apart, so the coordinate y and the coordinate y plus dy, there is only a finite length in the x direction, which is 2a. So if I integrate this formula over that finite length in the x direction, I will get the total charge that is at a particular, that is between y equal to y and y equal to y plus dy. I have only integrated over the x direction. I have not yet integrated over the y direction, because this is surface charge density, this is charge per unit area. To get the total charge, you have to integrate it over an area, but I have only integrated over a length. So I will get a charge per unit length. The charge per unit area transforms into a charge per unit length by, so the x dimension has been taken out, the x dimension has been integrated. So this becomes charge per unit length in the y direction. So thank you for watching. I will take up the C part of this problem in the next part of the video. So thank you for watching, and make sure that you understand, you can go back and understand any part that you have missed, but you should also try to think on your own. It would be better if you just take small hints from the video and then think on your own, in your own style, in your own words, because that would make that learning stronger. So thank you.